All right. So, good morning, everyone, and welcome to the new module that we will be discussing today. So, this will be the continuation of what we have last time, and it is all about transforming our time series to a supervised learning problem. Now, to give you a background of what we have been discussing, so last time we discussed about the introduction to time series. And from there, we learned that a time series is a sequence of data points organized in time order. And basically, we discussed the different types of or different ways that the time series can be utilized or used, such as we can use it for forecasting, can use it for stock market analysis, we can use it for anomaly detection, and we discuss about the different components of time series. It has three components, mainly the trend, the seasonality, and the residual. And then we discuss about how we can decompose uh, models, no, such as decomposition, multiplicative decomposition, and pseudo-additive decomposition. We also discussed last time how we can convert our time series into stationary time series. But what is stationarity? Now, stationary means the time series have no trend or seasonal effects. So we have discussed that there are many assumptions on the stationarity of a time series, no? There is assumption 1 where there is constant mean, assumption 2 where there is constant variance, and many instances. So those are the things that we discuss until we reach to a point that we were able to discuss some of the classical models, no, namely ARIMA, the autoregressive integrated model, no, which we have used for forecasting and evaluating our time series. So basically, we can apply ARIMA for forecasting, and we have learned that we can do forecasting using simple average. We can also use um, exponential moving average or equally weighted moving average. But there are issues, no? Uh, Instead of doing that, the most uh, applicable, the most applicable way to handle smoothing is the double exponential or the triple exponential smoothing, where actually there is a good result on the um, evaluation of our time series. Now, the way we evaluate our time series in terms of ARIMA is that we measure the efficacy of an estimate using the mean squared error. Sometimes we use the RMSE or the root mean square error. So those are the things that we have discussed so far. But for today, we're going to discuss how we can transform a time series to a supervised learning problem. And this way, we can actually make our time series as an input to our machine learning or deep learning algorithms or models. So in this lesson, you will know what supervised learning is and how it is the foundation for all predictive modeling machine learning algorithms. And then the sliding window method for framing a time series dataset and how to use it. How to use the sliding window for multivariate data and multi-step forecasting. So let's start with the supervised machine learning. Now, the majority of practical machine learning uses supervised learning, wherein we just know that in a supervised learning, everything is labeled. We have input variables that are labeled and output variables that are also labeled. And in this case, as an example, you can see that in order to get an output, we need to get the function of our input, which is x. So y will be equal to the function of x. And to be able to do that, we will use a mathematical equation or what we call an algorithm so that we will learn the mapping function from the input to the output. And in this case, you will see if we have 5 as an input, we have zero point 0.9 as our output. If we have 4, then our output is zero point 0.8, and so on. Now, supervised machine learning can be used, and we have been using supervised machine learning and deep learning in our previous classes, wherein we were able to classify. We used the machine learning or deep learning in some of the classification problems where the output variable is a category, such as it could be a red and blue, or it could be a disease or not a disease. On the other hand, we also have regression problems, no? When the output variable is a real value, such as temperature, currency, weight. No? So here in this example, we can see that this is a regression problem. Okay, we don't actually classify. So this will be an example of what we call a regression problem. Now let's talk about sliding window. So what about sliding window? Sliding window, um, it's a common technique. It's a common technique in, actually we use it in signal processing. We use it in machine learning for analyzing time series data. So sliding window is a method where it involves dividing a long time series sequence into smaller overlapping windows of fixed size, and then processing each window independently. So this can be useful for uh, tasks such as feature extraction, anomaly detection, and time series forecasting. Now, in order to implement a sliding window, we need to choose a window size. Now, for example, uh, one step, that's an example. No? It could be one time step, or it could be a 100 time steps, and so on. No? And a step size should also be uh, chosen. So therefore, there are two things that we need to choose whenever we are implementing sliding a window. The first is the window size, and the other is the step size. All right? So again, an example of that is in choosing a window size, it could be a 100 times steps, and in choosing a step size, it could be 10 times steps. So what happens is that we slide the window across the time series starting at the beginning. Okay? So in this case, you can see, imagine we have a time series as follows. No? In time 1, we have 100 as our measure. In time 2, we have 110. In time 3, we have 108. Time 4, 115. And time 5, 120. We can restructure this time series dataset as a supervised learning problem by using the value of the previous time step to predict the value at the next time step. So if we try to reorganize this time series, the data would look like this in terms of X and Y, where the X is our feature and Y is our target. So you can see at the beginning, we don't have a feature, but we do have Y. And then we have 100, and our Y becomes 110, and so on. Now, as you can see, when we try to implement a sliding window, we slide the window across the time series, starting from the beginning and moving forward in increments of the step size. And in this example, we have only one time step. All right? And at each position, we extract the values within the window and use them as input, no, to the next time step. Now, in terms of multiple variates, the number of actions recorded for a given time in a time series dataset matter. Traditionally, different names are used. For example, univariate time series and multivariate time series. So when we say univariate time series, these are datasets where only a single variable is observed at each time. For example, temperature per hour. The example in the previous section is a univariate times dataset. So this is an example. This is a univariate. However, if we take a look at multivariate time series, these are datasets where two or more variables are observed at each time. And this is an example framing a supervised learning problem wherein we have a multivariate time series. So you can see that the features x1, x2, and x3 are multivariate. We have only one output as y, but we do have multivariate time series. Now, how do we slide window with multiple steps? It's easier to understand. We are sliding on a window in only just one time step, and if only we have one window. But how do we do sliding a window in multiple steps? Now, the number of time steps ahead to be forecasted is important. It's traditional to use different names for the problem depending on the number of time steps to forecast. So when we say one step forecast, as you can see, this is where the next time step or t plus 1 is predicted. But when we have multi-step forecast, this is where two or more future time steps are to be predicted. So it could be t plus 2, t plus 3, t plus 4, t plus 5, and so on. Like in this case, if we have values of time and measure, such as this, we can reframe it as a two-step forecasting dataset for supervised learning with a window width of 1. So how do we do that? So we're reframing this so that we will have a multi-step forecast, meaning so that we will have two forecasts now rather than having only one forecast value. So we now have two forecast value at y1 and y2. So you can see that we are sliding the window width by 1. All right? So you can see the the measures of 100 was placed in our y1, and of course in the beginning we don't have x1, and the measure of 110 was placed on y2. Then we slide our 100 into our x1, we slide our y2 into our y1, and then we get the next value of 108, which is our third measure. And we do it until the end of our measures. And you will notice that at the end, no, at the end of the measure, which is 120 as our input value, we don't have y1 and we don't have y2 because we are expecting to forecast for our y1, which is step 1, and y2, which is our step 2. So therefore, in implementing a sliding window, it is important to understand, as I repeat, we need to choose the window size. We need to choose the step size. For example, if we have a time series with 1,000 time steps and a window size of 100 and a step size of 10, how many windows we can create? So we would create 91 windows of length of 100 because we are dividing 1,000 by 10. So with each window overlapping the previous one by 90 time steps, we can feed each window of data into a machine learning or to a deep learning model to make predictions or extract features. So basically, sliding the window can be used in a wide range of machine learning or deep learning algorithms. No, this includes regression models, classification models, and neural networks. No, for example, LSTM, which we are going to discuss later. And they are a very powerful tool, no, for analyzing time series data, and it can help to capture local patterns, trends within the data. Now, let's try to prepare our time series data for CNNs and LSTM. And in this lesson, we will learn how to transform a time series data into a two-dimensional supervised learning format. Now, before we can feed our data, our time series especially, no, we need to transform it in such a way that the machine learning or the deep learning model will understand. So that today we're going to discuss how we can transform a two-dimensional time series dataset into a three-dimensional structure suitable for CNN and LSTM. We will also know how to step through a work example of splitting a very long time series into subsequences ready for training for a CNN or LSTM model. So the overview of our lesson will be the following. We'll be starting to discuss about time series to supervise, and then three-dimensional data preparation basics, and then univariate work example. All right? So, again, as you can see from the this is an example univariate time series. And if you are looking at the basics of Python, we know that this is a list, no? And a list contains numbers. It could contain integers. It could contain a string value. And in this case, we have 1 to 10 as an example of a univariate time series. However, time series data requires preparation. No? Before we can use it to train a supervised learning model such as LSTM or CNN, no? We need to represent this time series, no? And we need to represent it as a vector of observations. And an example of a general supervised learning problem is in here, no? We have a sample input and then we have a sample output and so on. And we have discussed this a while ago that in order to get our output, we need to get the function of our input. Now, if you have a 10-step univariate series, we can express it into a supervised learning problem with 3 time steps for input and 1 step as an output. Like in this case, we have 3 time steps as our input, namely 1, 2, 3, and we have 1 step as our output. and our output here is 4. And then we slide the window, no? Discarding 1, we have now 2, 3, 4 as our input, and we have 5 as our output. Discarding 2, our next window, we have 3, 4, 5 as our input, and we have 6 as our output. This is an example of a univariate time series converted in such a way that the 10-step univariate series was expressed as a supervised learning problem with 3 time steps for input and 1 step as output. But we can do this easily, no? In Python, we can do this using the pattern that we have here, no? Here is a set of function that implements the behavior of splitting a given univariate sequence into multiple samples, no? Where each sample has a specified number of time steps and the output is a single time step. Now, if you don't understand the code here, we have a function, okay? And this function splits, no, a univariate time series. It splits it into input and output samples with a specified number of time steps as defined by the argument n underscore steps. Now, how does this function works? So basically, as you can see from the example, we have defined split sequence. So therefore, the name of the function is split sequence. And this function takes in 2 arguments. The first argument is the sequence, which is the input time series that we have. No, it could be a list of array and n number of steps as the second input parameter, which is the number of time steps in the input sequence that will be used to predict the output. Now, the function initializes, no? The function initializes 2 empty lists, namely x and y, which we are going to use to store the input and output sequences respectively. And then you can see that the function loops through each element in the input sequence, starting from the beginning. And for each element in the sequence, the function defines an end index, no? Which is the end steps, time steps ahead. Now, if the end index is beyond the end of the sequence, the loop will stop or the loop will be broken. Which means, that means there is no more to complete, no? There are no more complete input or output sequences to generate. So that's the end of it, no? But if the end index is within the bounds of the sequence, what will the function do? The function will extract the input sequence, sequence X, from the current element up to the number of steps, time steps ahead. And the output value, sequence Y, sequence underscore Y, at the end of the input sequence. So the input and output sequences are appended, no, as you can see there, it's appended to the X and Y lists respectively. And once the loop is complete, the function returns the input and output sequences as array. So that's how we can explain the following function. Now, if you try to define this function, no, given here is an example of a univariate time series in terms of rows and columns, no, as depicted in our example here. But what we are doing here is we try to represent, no, our data using Python and NumPy array. We have a NumPy and we are importing array here so that we can use it for our univariate data preparation. And as you can see from here, the function that I have explained is placed here, and then we will define our input sequence as follows, no? So we define our input sequence as an array of 10, 20, 30 up to 100. And then you can see that we are printing the shape of the series, and then we split the sequence, no? And we took the value of the series. So this will be provided here, the list which is an array, and then we will be using 3 as the number of steps. So because this will be the input, no? The series is the list of an array, and 3 here is the n number of steps. And then we will be printing the shape of the x and the shape of the y. And this is how it looks like, no? We printed how it looks like by looping and printing the range of x. You can see now that the shape of the series is 10, because we have from 10 to 100, and then the shape of x is 7 and 3, meaning we have 7 rows and 3 columns, and the shape of y is 7, right? So the data looks like this. So we have managed to prepare a univariate time series with time steps of which is equal to 3. So this data in this form can be used directly, no? This can be used directly, no? The shape that you can see from here, it can be used directly to train a simple neural network. Now, for instance, we can use this instance into a multi-layer perceptron. Now, the difficulty for many beginners comes when trying to prepare this for CNN and LSTM. Because in CNN and LSTM, we require the data to have a three-dimensional structure. And as you can see here, what we have produced so far is just two-dimension. No? Now, how do we prepare our two-dimension into a three-dimension? Now, remember that the input layer for CNN and LSTM models, no, which I will be discussing later, yung LSTM, no, we have already know CNN, no, and if we have an image of RGB, that's going to be a three-dimensional image. Now, the input layer for CNN and LSTM is specified by the input shape argument on the first hidden layer of the network. And these two can make things confusing for beginners because we may expect the first layer defined in the model the input layer, not the first hidden layer. For example, below is an example of a network with one hidden LSTM and one dense output layer. Right here, we don't see an input data because we did not specify the shape of the input data for this particular LSTM model. Now, it's very important to understand the three dimensions for CNN and LSTM. And the three dimensions, no, that we're talking about for LSTM layer so that we can implement LSTM are the following. We provide the sample, and one sequence is one sample. A batch is comprised of one or more samples. We also need to provide the time steps, which is one time step is one point of observation in the sample, and one sample is comprised of multiple time steps. And thirdly, we need to provide the features. So one feature is one observation at time step, and one time step is comprised of one or more features. So you can see from here, we have now an input shape of 3 by 1. So we have an LSTM with an input layer, and we have an output layer here. But we need to reshape, no, our input shape. It's because uh, the samples, or this is sample here, which is 3, and the number of feature is equal to 1. But we need to convert it in such a way that the LSTM will understand it as an input value. And the LSTM accepts an input value of the number of samples, number of time steps, and the features. Thus, we can now reshape our X as the following. So that means we need to reshape our two-dimension to three-dimensional shape, such as the number of samples, the number of time steps, and the number of features. Okay, this is another example of reshaping 2D to 3D. What's the most important here is that we should be able to convert our 2D into 3D, and there are many ways on how to do that. Now we can make this concept, no, this is concept, no, we can make it concrete with a work example. And right here, below here, we have an example of the complete code listing. And as you can see, the title of this code is to transform univariate 2-dimension to 3D. This is the same as we did, no, from the top or from above of the code that we have, wherein we have a series, we convert it into an array, and then we split. We use this function split sequence, inputting the series and inputting 3 as the number of steps. But right here below is the transformation. So therefore, we need to transform the shape of X in order for it to become acceptable as an input to an LSTM or CNN model. And how do we do that? Of course, by using reshape. We take the shape of the first index value of X and the second index value of X, and the number of feature is equal to 1. So here we have the number of samples. So these are the number of samples. The second shape is the number of time steps, and the third shape is the number of features, which is equal to 1. And then we print the shape, and as you can see, the two-dimensional shape of 7 by 3 becomes 7 by 3 by 1. This is an example output from reshaping the 2D data to be 3D. Now consider that you are in the current situation. Now, as you can see from here, where is our okay. So let's go back. Consider that you are in the current situation. For instance, you have 2 columns in your data file with 5,000 rows. Column 1 is time with 1 hour interval. And column 2 is the number of sales. And you're trying to forecast the number of sales for future time steps. So what we're going to do is to set the number of samples, the number of time steps, and the number of features in this data for an LSTM. So there are few problems here that we may encounter. Now, LSTM expects 3D input, and it can be challenging to get your head around it first time. Now, sequence length. LSTM don't like sequences of more than 200 to 400 times steps, and we have 5,000 rows. So the data now will need to be splitted into subsamples. And how do we do that? First thing that we need to do if we have a data like this is to load our data set using Panda series. No, we can use the read CSV. All right. For example, we have, in this example, we are not actually loading file name.csv. We know for a fact that we have 5,000 as our number of rows or number of samples. So we will define our data into a list, and then we define n as the number of samples that we have which is equal to 5,000. And then right here, you can see that we're looping on this n, no? We're looping on the range of 5,000 from 0 to 5,000. We're looping on it, and when appending our data as a list using the following features. I plus 1, and then the other one is I plus 1 multiplied by 10. So therefore, if we have a value of 1, and then here, the second value will be the value of 10, and so on. And as you can see from there, no, this is just an example of the data array that we have. No, but if we try to print, now because we just took the first 5 data here, no, and that is why you can see the first 5 uh, data that we have as an array. But here, you can now see that the shape of the array is 5,000 by 2, meaning this is 5,000 sample steps or time steps with 2 values per step. All right? Now, why do we need to drop the time column? Now, if your time series is uniform over time, there are no missing values, no, we can actually drop the time column. So meaning we cannot we can ignore the time column. In some cases of performing time series problems, no, we don't drop the time series or time element. But if you have a time series data that is uniform over the time, there are no missing values, we can drop the time column. If not, no, there are many things that we need to look up, no? Sometimes we need to input the missing values. Sometimes in order to fill some missing values, we need to calculate, no? Or we need to resample the data to a new time scale or develop a model that can handle missing value. Here, in this example, we just drop the first column. And as you can see from here, okay, we drop the time. Now we just drop the data here. So the data now that we have in this example is, or the shape of the data now becomes 5,000 by 1. Okay, so this is just a 2-dimension. Now we can split it into samples, no? So you can see here that we are doing a split up, no? The data that we have, we drop the time value here, and then we need to provide a splitting, no? So this is the sample of the splitting that we will do. For example, we can split the 5,000 by 200 so that we will have 25 splits. So you can see here, 200 will be the length that we will use to divide our data. Okay? So that means we will have a step over of we will have to have a step over the 5,000 in jumps of 200 or 200 per time steps. Okay? So you can see here that we are looping from 0 to n to the length. And then we append our samples, and then we printed the number of samples. We now have 500 because 5,000 divided by 200 is equal to 25. So that's our length for the number of samples that we have. That means we now have 25 subsequences of 200 time steps each. Okay, 200 samples of 200 time steps each. Now that we have now that particular sample, no, the LSTM will now be complete because we now have the number of samples, we now have the time step, and we now have the feature. So we have 25 samples as we have taken from our uh, operation here, and 200 time steps, and then one as our feature. But we need to convert our of arrays into with the shape of 25 by 200. And as you can see from here, we have managed to convert our list of array into a 2D numpy array with a shape of 25 by 200. So you can see now we see that we have 25 rows, 200 columns. This is interpreted in a machine learning context that this dataset has 25 samples, 200 features per sample. Next, we can use the reshape function to add one additional dimension for our single feature and use the existing columns as time steps instead. So you can see at the bottom, we have the reshaping of the data, that the length of our sample and the length and the number of feature will be equal to 1. We are reshaping it to convert our 2-dimension into a 3-dimensional feature. And that's it. No? The data can now be used as an input to any LSTM model or even CNN model. All right? Now, just some quick lecture on RNN and LSTM. So you can see here that we are already done with our lecture in preparation of our time series data for CNN and LSTM. But basically, we need to understand more about RNN and LSTM. No? So if you take a look at RNN here, the definition are as follows. No? RNN stands for recurrent neural network. It's a type of neural network designed for processing data. So in contrast to feed-forward neural network, which process data in a single pass to the network, RNN maintains a memory of previous inputs and use this memory to process current inputs in a sequential manner. Now, to understand that this clearly, okay, let's try to define our let's try to define recurrent neural networks and LSTM in such a way that we can use a practical example. Humans don't start thinking from scratch every second, right? For example, uh, you don't uh, you don't throw everything away and start thinking from scratch again. Now, our thoughts have what we call persistence. No, every time that we woke up in the morning, no, we remember what we did last time, no, yesterday or even some years back. We don't start from scratch. But if you remember, there is a movie from Adam Sandler. This is for 51st Dates, and the lady there, Drew Barrymore, every time she wakes up in the morning, she wakes up in the morning, everything resets. And the last time that her memory can recall is the last time before the accident happened for her. Okay? Imagine that you have a condition like that. Okay? This is not what's happening with us, no. Our thoughts have persistence. Now, traditional neural networks cannot do this, no. And it seems like this is one of the major problems or shortcoming for some traditional neural networks. Now, for example, imagine you want to classify what kind of event is happening at every point in a movie, no. It's very unclear how a traditional neural network could use its reasoning about previous events in the film to inform later ones. Now, RNN address this issue. No? RNNs are networks with loops in them allowing information to persist. No? As you can see from the image here, an RNN is a neural network that recurs. Kaya nga ang tawag sa kanya ay recurrent neural networks. Wherein the input, we have an input into our neural network. So computations happen here and then we have the output. And then what happens next, no? At the second point or at the second loop, our output becomes an in itself, no, in sequence number 2, and so on. We have sequence number 2, we have sequence number 3, and so on. So this is what we call current neural networks, no. You can see from there that the loop makes the recurrent network seem kind of mysterious, no. Why is it mysterious? Because if you think a bit more, it turns out that they are not that different in a normal neural network, because a recurrent neural network can be thought of as a multiple copies of the same network, no? And each passing a message to a successor. However, there's a limitation. I remember I place here a limitation for RNN. RNN is supposed to carry the information in time. However, it is quite challenging to propagate all the information when the time step is too long. For example, you have very long time step, no? So that means when you have a network that is too deep, no, it becomes untrainable. This is what we call the problem called vanishing gradient problem. Now this is where LSTM comes into play, because this LSTM is a type of recurrent neural network which is designed to handle long-term dependencies in sequential data. So LSTM believe to solve the problem of vanishing gradient, no, that limits the ability to capture long-term dependencies in a sequential data. And LSTM networks use a more complex memory cell structure that allows them to selectively retain or forget information from previous time steps. And the basic structure of LSTM cell includes 3 gates. So you can see that an LSTM has an input gate. It also has a forget gate and output gate. All right? So you can see what is the input gate. This gate controls how much new information is added to the cell state at the current time steps. And the forget gate, which determines how much the previous cell state is retained or forgotten. The output gate controls how much of the current cell state is used to produce the output at the current time steps. An example is given below. This is a real world example, but this is just the shampoo.csv. What we did here is to basically load it into a series, and as you can see, the series is very long. And then what we did here is to plot the series. So this is how it looks like. This is from 1901 to 1903. And the values are typically not stationary, no? It's improving. Uh, there is a trend, okay? Now, you can see that managed to use the split sequence function here, okay? And we managed to convert, no? We managed to convert our series into a three-dimension, no? Where, as you can see, the number of features that we have, or the number of times, is by 4, and the number of the number of series that we have is 32, and then the number of features that we have is 1. So this is the final output wherein this can now be applied in an LSTM. And here below here is an example of applying that particular example into an LSTM. And in this LSTM, we now have the following values, no? So we created our sequential model here, and our LSTM has 50 neurons. We use ReLU as the activation function, and our input shapes are the following. Okay, so for LSTM we have the number of time steps, no, the number of steps and the number of features. Where the number of steps is equal to 3 and the number of features is equal to 1. Then we input, we provided our output layer here, and then we compile the model. We use the optimizer Adam, and then our loss function is MSE, and then we fit the model. All right, we fit the model by 200 epochs, and then we demonstrated the prediction that if we have an input of 70, 80, and 90 as our input values of an array, we can predict our input, no, using the following. And as you can see from here, this is our predicted value. Is it a good prediction or not? No, we actually don't care about what it has predicted, whether it is a good prediction or not. What we have so far is just to prepare our time series data for CNN or LSTM. And this is what matters most, because this is one of the most important things that we need to consider, when we try to prepare or to use the application of deep learning into our time series. We really need to prepare our data and convert it in such a way that it will be properly uh, reshaped in such a way that it should be prepared in this manner, as we have discussed. Okay? So if you have some questions with our lecture for this morning, please feel free to put your questions in our public chat, or you can use the microphone if you have questions. Any questions?